With that said, let's have a look at the first part, where we look at character frequencies. Before we start with something more fancy, let's look at the simple ways how we represent strings in a computer in the first place. And this is all about, computers work with binary, but we like our alphabets with Latin letters or whatever other scripts. And so we need some way of going from these alphabets to a binary representation in the computer. And so what we need is an encoding function, which assigns to each letter of our source alphabet, say the English alphabet, some representation in binary. Now, we can't just use one bit. It will be a string of bits. We often have many more characters in our alphabets. In particular, if this is binary, that's kind of always true. One piece of terminology will call the binary string that encodes a single character the code word of that character. And what we'll first look at is a fixed length code, where every character gets the same number of bits assigned, a code word of the same length for every character. And then we'll generalize this to cases where this is no longer the case. And here's probably the simplest and most well-known fixed length code. That's the ASCII character set, character encoding. And it's just given here on the slide. So here's a binary pattern. And then behind the pattern is what letter it represents. The sensible letters start around here. So this is a space, right? That's why you can't see it. And then there's some punctuation marks, the digits, uppercase and lowercase letters. That's pretty much it. If you try to represent some other European languages or non-Western languages, you're pretty much out of luck. There's 2 columns of these weird control sequences. That comes from the fact that ASCII was invented when people had needle printers, and you used this. These are told to used to tell the printer where to move the printing head and things like that. So many of them don't make a ton of sense anymore. But we still use carriage return for starting the next line. A new line is there somewhere too. Well, can't find it. This is line feed. Well, you will know text files on Unix, Windows, and Mac are encoded differently in that the line ending, the new line character, is a different one in each case. That's using some of those. Apart from these weird control characters, it's pretty much a mapping from the English characters to a bit pattern. Each character is mapped to 7-bit, so you can represent 128 different things. What's good about these, they're very simple. And so encoding and decoding is almost instant. You can do this very close to the hardware, so it takes literally just one processor cycle. In terms of compression, this doesn't really compress much. It doesn't compress at all. If you have a text that consists of just all A's, it would need the same space as some complicated Shakespeare play, whatever. It's also not really flexible. If you notice you need other characters, you're out of luck. And so you have to invent a bigger alphabet and find a new encoding. And this has plagued much of the computing industry in, I guess, the 70s, 80s, before people started with Unicode. If we don't want to upfront fix the code length, we can do something else, and that also is not a new idea. We can assign code words of different lengths to the characters if we're a little careful. And here's a very old variable length code. That's the Morse alphabet. Or, as I learned, there's different ones, but this is the International Morse code, which has just the Latin letters and digits. And so I guess you know this. You can use this to send letters over like a wire or just by making sounds. And then the dot is a short node, and then the dash is a long one. And so one way to say if you want to encode, then you want to use this table on the left, where you find the next character that you want to encode, and you produce that sequence of tones. If you receive something, at least in your head, you probably want to do rather what this tree says, what this tree shows. You start in the root, and then you either hear a long sound or a short sound, and that makes you go into a different branch. And then there's the characters. If you end up at a certain point, then the characters tell you what letter that corresponds to. Okay? It's quite typical that we have two representations of a character code, where one is convenient for encoding and the other is convenient for decoding. And so if you were to implement a compression method, you often represent the code in different ways in encoding and decoding. A cute little side remark, and to wake you up as well. What's the coded alphabet size in the Morse code? So this is testing the terminology and a nitpick of Morse code. We had an amazing 41 votes for the first question. So pay close attention to which alphabet the question asks for. Okay, we're getting close to the number of people from before. Okay, let me show you what you've voted, and it's a few more down there. So this is a big peak for 36, and some votes for pretty much anything. So if you read the question carefully, it's about the coded text. So we're not asking about how many characters can you represent, not A to C plus the 10 digits. But why is the correct answer 3 and not 2? Because we have dot and dash. That sounds like 2. The thing in Morse, it is a little cheating. There's a third character, which is pause, end of a character. If people use Morse codes, they leave a little silent period between the characters so that you know when one character is over. And if you look at this decoding tree, you see immediately that you need this. Suppose I hear one short sound. How do I know whether I should continue from here down when I hear the next thing, or whether I should stop and say, oh, that was an E? There's no way for me to tell unless the other person gives me the pause to signal that this is the end of the character. So Morse code really uses 3 characters, the 2 shown here and a break, end of character. Okay? And yeah, you need this if you have a tree like this. That's another thing we'll come back to. There's one more variable length code that I bet you all know, and I bet most of you don't realize it's variable length. But if you thought about it for a minute, you notice it has to be. And that's UTF-8, or UTF-16 is similar. That's the standard way to code text files these days, since at least 20 years, I guess. It took a while on the web to convince everyone, but is a way to represent text files that can contain any Unicode character. And remember, there's some 150,000 of them, although most of them are not used very often. And so UTF-8 is designed around the idea that most of the time people use just the ASCII characters with a few extra characters from the full alphabet, like all your emoji. They're all just one code point in the Unicode alphabet. But if you send text, maybe the fraction of emoji is rising, but you still, by and large, on the text have more of the traditional characters. At least that's the assumption UTF-8 is built on. Okay, it can represent any Unicode character, and there's more than 100 or more than 256. So the UTF-8, 8 stands for 8-bit. It hopes to represent most characters with just 8-bit. But that would mean you can only represent 256 different ones. Doesn't work for all of Unicode, so it has to do something different. And what it does is it uses between 1 and 4 bytes for one character. The ASCII characters are encoded in 1 byte, and there's a leading 0. Remember, ASCII 7-bit, add a 0 in front, that makes 8-bit. So that's fine for representing all those with just a single byte. If you need any of the non-ASCII characters, then things are slightly more complicated. And in a sense, there's different regimes. There's the Unicode alphabet is broken up in different ranges. And depending on where it is, so this is the Unicode character in hexadecimal. If it's ASCII, then it fits below this. So 7 and F, that's 7 ones written in hexadecimal. If you're above that, but below the next more 4 more bits, then you get represented with 2 bytes, and the X's are replaced by the actual code point, and so on. So it's, I know it's a bit tedious to read. And you see that there's a special way to signal how many bytes each character will take. So if you read Unicode, the next byte, if it starts with a 0, you know it's just a single byte character, an ASCII one. If it starts with 2 ones and then a 0, you know it's 2 bytes that are coming. And you have to puzzle out the X's to get the character. And each byte that is not the first one is starting with 1, 0. And here you have 3 or 4 ones to signal the small bytes coming. Why do you think do we need this 1, 0 here to signal that this is, why do we do this in the next bytes? We could have just left it out because this already tells you how many bytes are following. Any guesses? So people do this for convenience. If you jump into a Unicode text at a specific byte index and you see that the byte starts with 1, 0, you know you're not actually looking at the beginning of a character, but you're somewhere in the middle of the previous character. So you know not to start to decode from there, and instead you skip over all the bytes that start with 1, 0. It's just a way to trade space for convenience. You could have done a fewer bits if you were just after compression. But since this is also used as a way to represent strings in memory and compute over them, it turns out it's more convenient to spend a few bits here to make access more efficient. All right, so UTF-8 combines the space efficiency of ASCII for the characters where you just need this English language letters. But you have a way to represent any other characters when they occur, just using a little more space than for those. So that's one example of a variable length code that you've probably been using all the time without maybe thinking about it too much. The flexibility does come at a price. If you use a code that has variable length code words, you can get into trouble. And I want to illustrate the trouble on an example. Suppose you have this, this code. So that assigns to the 4 letters in our alphabet some code word. Now I can use this to encode a string like banana into this binary representation. And you see the B corresponds to 110, so I write 110, then comes an A, single 0, and so on and so forth. Okay? I hope the encoding step is clear. You just concatenate all the code words for the characters. Now, if we try to decode this bit pattern, there's another way to read it. We can say this could be BA, but then SS instead of na. Because 100 is also the code for S and for N and A concatenated. So there's 2 ways to decode. That's not good. So it's an ambiguous code. And of course, if you look at this, you immediately see that if you write an NA, it leads to the same code as a single S. So there's trouble ahead for sure. But if I just showed you this code and asked you, is this code good or not? It might not have been completely obvious that it is flawed. In this example, of course, it's clear, but how can we avoid creating codes that have this ambiguity? We can't tolerate this. It's not a way we can live with. We want to be able to reconstruct the source text exactly. In general, this is relatively hard, but there's a simple sufficient condition. What made this code nasty is that one code word, 10, is a prefix of another code word, 100. So when you decode and you read this 100 pattern, you start reading 1 is not a code word, so I can't stop. 10 is a code word, so I could stop, but I could also continue. And at this point, the decoder doesn't know what to do unless you help him out. If, by contrast, our code has the property that no code word is a prefix of another code word, then the decoder never gets into this problem. It always knows as soon as it has found a code word, it can stop, and it's unique what it decodes to. And so if the code is prefix free, which means no code word is a prefix of another, it is what people call instantaneously decodable. So as soon as you read one code word, you can decode that and go on to the next one. And that also implies that it is uniquely encodable. I just want to point out that there are uniquely decodable codes that are not instantaneous. So you can come up with some complicated code where after 10 characters later, you discover, oh, this is a dead end. I shouldn't have gone this way. But if I take the other way, the other option of parsing this, I would have succeeded. You can build something like that, but it's not really any good. It only makes decoding slow. So we will not look at those. We'll only look at prefix-free codes. But I wanted to point out that uniquely decodable is a weaker assumption than prefix-free. But we'll live with prefix-free. It's good enough, and you'll see in the next section what good enough means. If we have a code that is prefix-free, there's a convenient way to represent it graphically, and that's the code try. So here's another example of a code, and this one is prefix-free. As you may try to check briefly, no code word is a prefix of another code word. And an easy way to check this is to draw the try. So you just take the code words and build the try of this set of strings. Remember, we talked about tries last unit at length. So in the terminology of the last unit, this is the simple try without any compaction, no suffix trees, right? Nothing fancy. The nodes in the tree just have one child for each possible alphabet character, and you advance with one character on each edge. If you do this for this code, you will see that all the code words lead you to a unique leaf. And that is the signal that the set of strings is prefix-free. And if you remember from the last unit, that was pretty much exactly what we did there as well. We enforced prefix freeness by adding this $sign at the end. And here we say, no, we don't want to add another symbol to our alphabet. We just want to pick carefully a set of strings that already happens to be prefix free. Okay, so the way to check if a code is prefix free is draw the try and check if all the code words are in leaves. And the code try is also a convenient way to decode. Let's do an example. If we want to encode this string, then we want to use the table up here, because there we are given by the character what is the code word. So A goes to 0, 1. Then N is 0, 0, 1. And space is 3 zeros, and so on and so forth. Okay, I think that direction is easy enough. The decoding is a little more interesting, so let's do this example at least. We process this text left to right, but we traverse in the try while doing that. So we read the first one, and then the second one, and that brings us to a T. So these two correspond to T. And as soon as I reach the leaf, I know I found the first character. So I cut off these first two, and then start at the root again for the next character. This time I see 1 and then 0 and then 0. So it has to be an O. 1, 0, 0, that's the next cut. And there's the O. One more. We start at the root, 0, 0, 0. So the next is a space. Notice there was never ever any chance for going wrong. There was no choice. There was no ambiguity. I just follow the path. I ended up in a leaf, and then continue from the root again. Okay? And here are the examples in full detail, just to check. So that's the way we want to think about character codes. I'm only really interested in the prefix-free ones, so it's the same as saying I have a code try of the code words. And that also happens to be convenient for decoding as a data structure to represent the code. Okay, if in general there's the question, how can decoding know what code to use? And that is a real problem if you think about text files and character encodings. You may have seen websites where certain characters just render as some gibberish. And the reason for that usually is that whoever wrote the website was still living in the 90s and used some non-Unicode encoding of the text characters. And your browser, being from 2022, thought everyone has to use Unicode or UTF-8 encoding unless they tell me something different. And so it interprets the file as if it was Unicode, but it actually wasn't. And so some characters look up wrong. It doesn't work. It doesn't break the ASCII characters, but it breaks some others. The reason why this went wrong is someone has to tell the decoder what code was used to encode so that it can apply the right decoding. For ASCII or UTF-8, at least everyone in the world agrees what ASCII is and what UTF-8 is. So it's kind of easy. You just have to tell someone, use UTF-8, and you'll know what's going on. If we use a code like on the previous slide, a custom code like this, I have to tell the decoder what the code was. Otherwise, it wouldn't know what to do. And it turns out this is really a question of the application, whether the code is part of the coded text or not. If the code is fixed and known outside externally, that's what we use for text files and for Morse. If you send your SMS by beeping, then you assume people would recognize that this is 3 short, 3 long, 3 short. Then we don't need to transmit the code. We just assume everyone knows the encoding. If we use what we'll call static coding, where we use the same encoding for the entire text, then we might have to transmit the code because the code is custom for the specific text. But at least it doesn't change while decoding. there's even wilder things that we'll call adaptive coding, where the way you encode the character keeps changing while you're going. In that case, you'll have to somehow tell the decoder how the code changes. And this will often be implicitly in the code. But this is what makes these codes a little more tricky. Now we'll see example of each of these. So this is just for the distinction of the terminology. Fixed versus static. So fixed coding means everyone in the world knows what that code is. Static means it's the same code for the entire text, but the code still depends on the text. And adaptive is anything else.